All right, let's get into it. Today, we're going to break down how some seriously advanced data engineering is being used to make sense of the criminal justice system. And this isn't just about crunching numbers, it's about architecting systems that can handle absolute chaos to try and build a better world. This line right here, it really sets the stage perfectly. The work we're about to explore isn't just some technical exercise. It's about taking hardcore engineering principles and applying them to a system where the stakes are unbelievably high, because every single data point represents a human life. And that really gets to the heart of it, doesn't it? The gravity of this data. When you're building systems for justice, you have to truly feel the weight of the information you're handling. Behind every single row in that database, there's a person, there's a family, there's a whole story. Now, here's what's so fascinating. The biggest problem isn't that it's big data. Nope, it's chaotic data. The data landscape in the justice system is just a mess. It's fragmented, it's inconsistent, and it's missing all the simple connections we take for granted everywhere else. It's like trying to build a single puzzle, but the pieces are from a dozen different boxes. Okay, so let's dig into that. What makes justice data so uniquely chaotic? Why is it such a beast to work with?
So check this out. This is the core of the problem. A single person's journey, what's called a criminal justice episode, is spread across at least 5 completely disconnected systems. The sheriff's office, the county jail, the state court, the Department of Corrections, they all have their own databases. And here's the kicker. There's no shared ID to link a person from one step to the next.
And that right there creates this massive engineering headache, the identifier problem. How on earth do you prove that John Smith, who was arrested and put in a county jail record, is the exact same person as Jay Smith, who shows up in a state court filing a month later? You can't just do a simple database join. It's literally impossible.
The solution is a really cool technique called probabilistic record linkage. The best way to think of it is like super sophisticated pattern matching. Instead of looking for a perfect ID, the system acts like a detective. It calculates the statistical probability that 2 records are about the same person. Using clues like fuzzy name matches, dates of birth, and even accounting for typos, it lets us connect the dots with actual mathematical confidence.
So as you can see, solving a problem like this takes more than just some clever algorithms. It demands a totally different engineering mindset. You need a toolkit built from the ground up for resilience and for reproducibility. Just imagine this scenario. You're scraping years of court records, and it's a process that's going to take 12 full hours. You get to hour 11, and the connection drops. Do you have to start all over again? A simple script would absolutely force you to. You'd lose half a day's work. It's a catastrophic failure that just screams for a more robust approach. And here is that elegant solution, the lake-first strategy. The whole architecture is built assuming that failure is inevitable. So step 1, fetch. Just grab the raw, unaltered data, the messy HTML page itself. Step 2, store. Immediately save that raw file in a central data lake, like a digital warehouse. Only then, in step 3, do you try to parse it. Now, if your parser crashes, who cares? The raw data is safe and sound in the lake. You just restart the cleaning step without losing 11 hours of work. Now let's talk about another classic issue. I'm sure you've heard this one. An analyst runs a script, gets a result, and publishes a big report. But when another researcher tries to run the same script, they get a different answer, or maybe it just crashes. This is the dreaded works on my machine problem, and it completely erodes any trust in the findings. The modern professional standard is to build what are known as reproducible analytical pipelines, or RAPs. So instead of those brittle scripts that only work for one person, you build these robust automated pipelines using tools like Docker. This guarantees that an analysis run today will produce the exact same mathematically identical result 5 years from now, no matter who runs it or where. This whole philosophy treats the data's history as sacred. It's like you're creating a living constitution for the data, where every single transformation is recorded in a log that can't be changed. You don't just have the final numbers, you have a perfect, auditable history of exactly how they came to be. So when you put all these engineering principles together, planning for failure, ensuring reproducibility, and tracking that history, you end up creating something much bigger, an architecture of trust. This is how you build a system that can handle incredibly sensitive data ethically and securely. Here is a perfect example of the kind of dilemma you face.
A person has their criminal record legally expunged. So if you delete the record from your database, you break your historical data, and your trend analysis is suddenly wrong. But if you keep it, you're violating that person's privacy and a direct court order. So what do you do?
Well, the solution is a really smart method called tombstoning. You don't actually delete the record. Instead, you just mark it with a special flag, a tombstone, that makes it invisible to all standard analysis and queries. The data is still there for historical integrity and audits, but it's logically inaccessible. It's a perfect way to balance the need for an audit trail with the legal requirement for privacy.
Building this trust goes even deeper. Real modern security isn't just some policy document. It's written in code. This means getting rid of leaky static passwords and using temporary tokens instead. It means giving every single process the absolute minimum privilege it needs to do its job. When your security rules are literally defined as code, they become auditable, version-controlled, and almost impossible to misconfigure. It's a fortress built of logic. Okay, we've gone through some pretty deep technical concepts here, but let's bring it all home and connect this engineering back to the real-world impact it has on policy and, most importantly, on people.
Because at the end of the day, it all comes down to this. Rigorous engineering builds trust. And trusted data, data that is proven to be accurate, reproducible, and secure, is the single most powerful tool we have for advocating for better policy. Without that trust, the numbers are pretty much meaningless.
And you can see the direct impact right here. That probabilistic linkage we talked about, that gives us accurate counts, so we finally know the true scale of the system. Those reproducible pipelines, they create trustworthy research that policymakers can actually rely on. And that architecture of trust, with methods like tombstoning, protects the very people that the data represents.
This leaves us with a final, powerful question. We've seen how thoughtful, rigorous, and even empathetic code can build an architecture of trust for something as complex as the justice system. So if it's possible here, where else can these principles be applied to solve our world's most challenging problems?